Well, hello students, welcome back to Mathematics Specialist class with me, Mr. Alfie. In this video, we're going to learn about complex numbers. Let's check this video out.
We already know what real numbers are. These are the numbers that can be represented on the number line. We also know that real numbers can be broadly classified as rational and irrational numbers. Rational numbers are those that can be represented as ratio of two integers with no common factor. Irrational numbers, on the other hand, cannot be expressed as ratio of two integers, and when expressed in decimal notation, they are non-terminating, non-recurring decimals. Are there any other kinds of numbers? Numbers that we haven't looked at yet? Before you answer that question, let me ask you another one. Can you think of a number which when squared results in a negative number? Yes, a number which when multiplied with itself gives a negative number. You'd have probably tried a few options. 3 times 3 is 9, positive. Negative 5 times negative 5 is 25. Again positive. Negative root 3 times negative root 3 is 3, positive again. No luck. We'll come back to this. Don't worry. So we've studied quadratic equations in middle school. We know that if x squared minus 9 is equal to 0, x is either equal to 3 or negative 3. Now try to find a solution to x squared plus 1 equal to 0. Or do you think there's no solution to this one? Don't worry if you couldn't get the answer to these two questions. Let's understand the situation now. Whenever we considered the square of a number, say x, the result was always positive, whether the number x was a positive real number or a negative one. We always got a positive result. And we had learned that a negative number did not have a square root. So if we had a number like negative 9, we said that its square root did not exist. Do you remember that while finding the solution of a quadratic equation using the formula, if the discriminant b squared minus 4ac was negative, we said that there are no real roots of the quadratic equation. Based on what we had studied earlier, x squared plus 1 equal to 0 will not have any real roots as the value of discriminant is negative 4. Why did we do this? What was the problem here? It's easy. As the square root of negative 1 did not exist for us, we said that there was no solution for the equation x squared plus 1 equals 0. However, in the 16th century, it was a mathematician named Cardan who first started thinking about solutions of quadratic equations with negative discriminants. Soon, others started too, but it was Euler in the 18th century who gave the square root of negative 1 a symbol I and called it the unit imaginary number. These were termed so as they were thought to be impossible and just something we imagined. So I was assumed to be a number whose square is negative 1. Now you'll be able to answer the two questions. Can you think of a number which when squared results in a negative number? Yes, it's I. If square root of negative 1 is I, what is I times I or I squared? It is root negative 1 times root negative 1. That gives us negative 1. There you go. We got a negative number by squaring a number. And the next question was, can you find a solution to x squared plus 1 equal to 0? The answer is yes. Transposing 1 to the right-hand side, we get x squared as negative 1. Taking the square root on both sides, we get the value of x as root of negative 1 or minus root of negative 1. That is plus minus I. So what we learned in school wasn't incorrect. This equation has no real roots. Yes, it has imaginary roots. We understood the concept of a unit imaginary number I. It is the square root of negative 1. If we square it, we get root of negative 1 times root of negative 1, which equals negative 1. The square of the unit imaginary number is negative 1. Well, let us now try to work out more powers of I. What will be I cubed then? I cubed is I times I times I. We can write it as I squared multiplied by I. Now as I squared is equal to negative 1, I cubed is negative 1 multiplied by I or negative I. So the value of I cubed is negative I. You can now similarly work out fourth power of I. The fourth power of I can be written as I squared multiplied by I squared. This is nothing but negative 1 multiplied by negative 1. And we already know that negative 1 multiplied by negative 1 is 1. Hence the fourth power of I is just 1. So I squared is negative 1, I cubed is negative I, and fourth power of I is 1. Can you similarly work out further powers like 5th, 6th, 7th and 8th powers of I? Try it out and you will observe something interesting. And this is what we would get. Notice the cyclical pattern in the powers. I, negative 1, negative I, 1, and then again I, negative 1, negative I, and then 1. This is one way in which we can understand it. First power, second power, third power, and fourth power. Then repeat. Fifth power, sixth power, seventh power, and eighth power. And this will go on. So what is I? It is just a unit imaginary number and is equal to the square root of negative 1. Why do I keep saying the word unit? To understand that, let's look at an example. What will the square root of negative 9 be equal to? If we try it out on a non-fancy calculator, it would say that the input is invalid. That's because most calculators are not programmed to use imaginary numbers. So how do we understand the square root of negative 9? It can be written as square root of 9 times negative 1, right? And we know a property of exponents which says that square root of a times b is equal to the square root of a times the square root of b. So this can be written as square root of 9 times the square root of negative 1. The square root of 9 is 3 and square root of negative 1 is I. So the square root of negative 9 is 3i. This is 3 times I. And this is also an imaginary number. But it's not a unit imaginary number as it's 3 times I. But the unit number I is 1 times I and hence it's called a unit imaginary number. Basically, any real number times I is an imaginary number. For instance, this is how we would write square root of negative 121 over 49. We get 11 over 7 times I. It's a real number times I. So numbers like 0.145i, 16.25i, minus cube root of 7i are also imaginary numbers. An imaginary number is simply b times I, where b is a real number and I is the imaginary number. We learnt that it is possible to have square root of a negative number, but it involved using a new number I which is equal to the square root of negative 1. These numbers are called imaginary numbers and could be of the form bi, where b is a real number and I is equal to square root of negative 1. Numbers like I, 2i, negative 4i are all imaginary numbers. What if we have a number like 3 plus 7i? Will this be an imaginary number? Well, we can be sure that this part of the number is imaginary and this part is a real number. So this is a mix of real and imaginary parts. And this is what we call an example of a complex number. Real plus imaginary gives us a complex number. It's of the form a plus bi, where a and b are real numbers and I is the unit imaginary number. Now let's play around with this basic form. Observe that when a is equal to 0, what is left will be an imaginary number. And when b is equal to 0, we only have a real number. So what are the real and imaginary parts in the basic form of a complex number? A is called the real part and bi is called the imaginary part. Now let me ask you something interesting. When will the two complex numbers a plus bi and c plus di be equal? They will be equal only if both the conditions are satisfied. First, A is equal to C, and second, B is equal to D. Yes, only if A is equal to C and B is equal to D will the two complex numbers be equal. Real parts equal and the imaginary parts as well are equal. In the previous video, we learned about adding complex numbers. To add two complex numbers, we simply add the real parts separately and imaginary parts separately to get a new complex number. How can two complex numbers be multiplied? Let us multiply 7 plus 2i with 3 plus 4i. We know that a times b plus c will give us a times b plus a times c. It's the distribution property. So this can be written as 7 plus 2i times 3 plus 7 plus 2i times 4i. Now focus on the first part. 7 plus 2i times 3. 7 times 3 plus 2i times 3. 21 plus 6i. The second part is still pending. How do we account for multiplication of 7 plus 2i with 4i? This added times 4i does not make sense. But we can still use the distribution property here. Multiplying 7 plus 2i with 4i, we get 28i plus 8 times I squared, which is nothing but 28i plus 8 multiplied by negative 1. This is nothing but 28i plus negative 8. This expression equals the product of these two complex numbers. To get the final expression, let's add the real parts and the imaginary parts separately. We get the real part as 21 minus 8 and imaginary part as 6i plus 28i. Hence, 7 plus 2i multiplied by 3 plus 4i gives us 13 plus 34i. Let us pick up two more complex numbers, 3 plus 5i and negative 2 plus 4i, and work out their multiplication. We can use the distribution property here to write this as 3 plus 5i times negative 2 plus 3 plus 5i times 4i. 3 times negative 2 is negative 6 and 5i times negative 2 is negative 10i. We get negative 6 minus 10i. Similarly, 3 plus 5i multiplied by 4i will give us 12i plus 20i squared. As I squared is negative 1, this can be written as 12i minus 20. And the last step is to add the real parts and the imaginary parts separately. We get negative 6 minus 20 or negative 26 as real part and negative 10i plus 12i or 2i as imaginary part. Hence their product is negative 26 plus 2i. In both the cases, we saw that a product of two complex numbers gave us another complex number. Is that always true? Keep this question in mind and try solving the next example. Try multiplying 2 minus 7i with 2 plus 7i. Let's look at division of a complex number by another. Before we move on to complex over complex, let's see an example of complex over real. Is 6 plus 9i divided by 3. This should be easy. We know that dividing a number by 3 is equivalent to multiplying by 1 over 3. Hence, dividing 6 plus 9i by 3 is equivalent to multiplying 6 plus 9i by 1 over 3. We get 6 over 3 plus 9i over 3. That will equal 2 plus 3i. So dividing a complex number by a real number is easy. How about dividing a complex number by an imaginary number? Say 6 plus 9i over 4i. Before we solve this, let's understand what 1 over I means. Not very comfortable having I in the denominator. So how can we get rid of it? It's easy. We can multiply the numerator and the denominator by I. That gives us I over I squared. And I squared is nothing but negative 1. And I over negative 1 is nothing but negative I. So 1 over I is equal to negative I. Now let's proceed with the problem. Dividing 6 plus 9i by 4i is equivalent to multiplying 6 plus 9i with 1 by 4i. So this will give us 6 over 4i plus 9i over 4i. As we saw that 1 over I is negative I, this can be written as negative 6i over 4 plus 9i over 4i. Simplifying this will give us negative 3i over 2 plus 9 over 4. As we write a complex number with the real number first, this is 9 over 4 minus 3i by 2. So dividing 6 plus 9i by 3 gives us 2 plus 3i. And dividing 6 plus 9i by 4i gives us 9 over 4 minus 3i by 2. Clearly, dividing a complex number by a real number or an imaginary number is quite easy. How about dividing 6 plus 9i by 3 minus 4i? This is a case of a complex number divided by a complex number. Just remember one thing in general. None of us like having I in the denominator. It just doesn't look perfect. So can we get rid of I in the denominator without changing the value of the overall expression?
What is the conjugate of a complex number? Let Z is a complex number where Z equal to A plus BI. A is a real number component of Z and BI is imaginary number of Z. Z conjugate denoted like this one equal to A minus BI. You simply just need to multiplication imaginary number in Z with negative. For example, let Z equal to negative 3 minus 4i. So Z conjugate equal to negative 3 plus 4i. Now, I want you to open example 4, chapter 13 in your book. And based on this example, I want you to do exercise 13b, number 27.
We had observed that multiplying a complex number a plus bi with its complex conjugate a minus bi resulted in a squared plus b squared, which is a real number. So to get rid of I in the denominator, we need to multiply it with its complex conjugate. And to keep the value of the fraction unchanged, we will also have to multiply the numerator with the same complex conjugate. So we multiply the numerator and the denominator by the complex conjugate of 3 minus 4i, which is 3 plus 4i. This makes the numerator as 6 plus 9i multiplied by 3 plus 4i and denominator as 3 minus 4i multiplied by 3 plus 4i. The numerator here becomes a classic case of multiplication of two complex numbers. And the denominator is a case of multiplication of complex conjugates. Let's simplify the numerator first. It will equal 6 plus 9i multiplied by 3 plus 6 plus 9i multiplied by 4i. This will give us 18 plus 27i, and this gives us 24i plus 36 times I squared. That will be 24i minus 36. Hence, the numerator is addition of 18 plus 27i and 24i minus 36. Adding the real and the imaginary parts separately gives us negative 18 plus 51i. That's our numerator. Now let's move on to the denominator. The denominator is 3 minus 4i multiplied by 3 plus 4i, which is nothing but 3 squared plus 4 squared. 9 plus 16 equals 25. Hence, dividing 6 plus 9i by 3 minus 4i gives us negative 18 plus 51i divided by 25. That can be simplified to negative 18 by 25 plus 51i by 25. Let's review what we did very quickly. When we divide a complex number by another complex number, we multiply the numerator and the denominator with the complex conjugate of the denominator. That will help us eliminate I in the denominator.